Okay, the last video in our series features another discrete random variable distribution. It's called the Poisson distribution, and this starts on page 174 of the text if you want to follow along and look into more details for it. But the big factor in the Poisson distribution is this given interval over space or time concept. So a Poisson random variable counts the number of occurrences, which again we'll call successes, of a certain event over a given interval of time or space. So if I want to look at predicting the number of cars that'll pass over the George Washington Bridge over a certain time, or the number of schools of fish in a 100 square mile area, you would use a Poisson distribution. So in business, especially in things like retail, the Poisson distribution comes up a lot, and you'll see our example will feature an example of this. A couple of things about this distribution. Its probability of successes is consistent over any interval of equal size. So if I look at a 2 hour span or a 3 hour span, anything like that, regardless of the span's location, it's always going to be a similar probability for each one of the individual instances. And the probability of success is proportional to the size of the interval. So the bigger the interval or the smaller the interval, the likelihood of success needs to adapt appropriately. Obviously, if an interval is open for a longer period of time, it's more likely to occur over that interval. So our success needs to accommodate that. So this is the formula for it. It's, again, a little ugly, but it's pretty straightforward once you understand all of the pieces. So for a Poisson random variable, the probability of x successes of a given interval is equal to this equation here. Here, the e value is the natural base. It's the number 2.718 roughly. This is a common button that you'll have in your calculator. It's a number. It's a number similar to pi. It's an irrational number. The mu here is, of course, our average. That'll be given to us, or we'll have to either calculate that. So it's e to the negative mu times mu to the x, again here the average, raised to the number of successes that we're looking at, divided by the factorial of the number of successes. So I think that it's best to see this again in a problem and really see how this formula can work for us. So imagine that we're a coffee shop manager, and they see that during an average 5-day work week, a typical customer visits, again, on average, roughly 3 times in 1 week. So if you're like a Starbucks or, again, a coffee shop, and you see a customer returns roughly 3 times in a 5-day work week, I want to ask a couple of sort of questions. So first off, what is the probability that a customer visits the coffee shop 5 times in a 5-day work week? So they visit maybe once a day. Similarly, what is the probability that a customer visits a coffee shop no more than 2 times in a 5-day work week? Or on the other hand, at least 3 times in a 5-day work week. So this will be really helpful for us if we're a manager determining how much staff we need to have. If we know what our clientele and how frequent they're going to occur, and we can then adjust our numbers somewhat accordingly. So let's answer first this question here. The probability that a customer visits the coffee shop 5 times in a 5-day work week. Well, in this example, we know that our average is going to be 3 times per 1 week. So that means that the mu in this case that we're looking at here, the mu is going to be equal to 3. And that's true for all of these circumstances. And now the x value that we're looking at is 5 times in a 5-day work week. So what I'm going to do is plug in mu equals 3, and I'm going to plug in 5 for x. And when I calculate all of these things individually, so e raised to the negative mu, e raised to the negative third is 0.0498. Again, you can just use that in your calculator. Okay, mu to the x, so 3 to the 5th is 243 divided by 5 factorial. Remember, that's 5 times 4 times 3 times 2 times 1 is equal to 120. So the probability, if the average customer comes in 3 times per week, the likelihood that a customer will come in 5 times in 1 week is roughly 10%, pretty high, so 0.010. And that's why the Poisson distribution really holds a lot of power to it, is that the formula can be somewhat random, but it can tell us a lot about likelihood beyond just what we know, especially if we're looking at a particular interval. So the second question is probability that a customer visits the coffee shop no more than 2 times in a 5-day work week. So that means that they can visit either no times, so the probability that it's less than or equal to 2. That's, again, a cumulative probability. So we're looking at the probability that they don't occur, they don't come by ever. They come by maybe once in the week or twice in the week. So what we can do is look at each one of these sums individually, and we can perform the Poisson distribution or calculate the Poisson probability for each one of these occurrences. So if I look at the probability that they don't come at all, I would plug that into the Poisson formula. I can do they come only once or they arrive twice. And I can add up those subsequent probabilities. So each one of these is just an exercise in calculation. Be careful on how you plug everything in and calculate. But either way, the sum of all of those things is equal to 0.42. So the likelihood that a customer, if they come in roughly 3 times a week on average, the likelihood that they'll come in at most twice that week is 0.42 or 42%, relatively high. Okay. Finally, the probability that they visit the coffee shop at least 3 times in a 5-day work week, well, this becomes a little bit trickier. If they're arriving at this coffee shop at least 3 times, that means that they can come to the coffee shop 3 times in the 1 week, 4 times, 5 times. They may even come multiple times a day, so 6 times, 7 times, 8 times. That can be really, really cumbersome to calculate. Instead, what we're going to calculate is the complement. So if the probability that they arrive at the coffee shop more than 3 times or more, well, that's equal to them arriving 1 minus the probability that they only arrive less than 3 times, or what we calculated in the previous event, because it's a discrete variable. So the probability, again, that they arrive more than 3 times is 1 minus the probability that they only arrive twice or once or no times at all. So that's going to be 1 minus that probability that we calculated in the previous example. So 1 minus that probability that they calculated, the 0.4233, is equal to 0.5767. And again, that's answering that the probability of a person coming to the coffee shop at least 3 times, but if not 3 times or more, that probability is about 58% rounded, which is relatively high. So again, we have this distribution, this discrete random variable distribution called the Poisson distribution that looks at the number of occurrences in a given time or a given space. It has a formula based on if we know the average of that, and depending upon the number of successes we would want to sort of measure, that would determine our probability by simply plugging in the formula here and maybe even getting a little bit clever with the complement. And that's the last part, the last type of distribution that we're actually going to talk about, discrete distribution that we're going to talk about. Usually from here on out, we're going to focus more now on continuous distributions, and that would be the next chapter. So hopefully you enjoyed it.